What is a qubit? A qubit stores information like a bit in classical computers. That is why it is called a quantum bit, or short, a qubit. The usual explanation says that a qubit can hold both states, 0 and 1, at the same time. That's not wrong, but it is a simplified picture and does not reflect the infinite value space that actually opens up in a qubit. This property is used in quantum machine learning, where you can encode a full variable, for example a feature like the end-of-day Bitcoin price, into one single qubit, a very efficient way to use quantum resources. The qubit is the core of any quantum computer. It is the source of its quantum behavior. Everything else in the machine is more about manipulating, linking, and operating qubits. Superposition, entanglement, quantum interference. All of these phenomena are rooted in the characteristics of the qubit. Before we dive deeper, it's worth asking, how are qubits actually built? Physically, qubits can be realized in different ways. Some use superconducting circuits like IBM with their Heron processor or Google with Sycamore. Others rely on trapped ions, as in the approaches of IonQ and Quantinuum. Another path is neutral atoms arranged in optical grids, pursued by companies such as Pascal and QEra. There are also photonic qubits, which Xanadu uses in their Borealis system. And finally, there are silicon spin qubits, an approach researched by Intel and the Australian group Silicon Quantum Computing. Each of these technologies has its own advantages and disadvantages, such as energy consumption, stability, error rates, scalability, or connectivity between qubits. Top physicists and engineers are working on these competing designs. Unless you are directly involved in quantum hardware development, you quickly get lost in the details of these discussions. Fortunately for us who just want to program quantum computers, this is not crucial beyond some fine-tuning when we talk about error mitigation or scaling. For the quantum coder, it is best to assume all types of qubits are functionally equivalent. Let us treat them as black boxes. Regardless of how a qubit is built, what really matters for us as programmers is how it behaves when we use it. And the most fundamental action we can take is to measure it. A qubit can be measured, obviously. Whenever you measure a qubit, you will always get either 0 or 1. Nothing in between, never both. Just 0 or 1 every single time. After a measurement, the qubit's state is erased. You can measure a given state only once. To re-measure, you need to prepare the qubit again and bring it back into the same state. So far so good. Now we repeat the measurements of a qubit prepared in a specific state. We again only get 0 or 1 each time. But if we track the results on a histogram, placing a tile on the pile for 1 whenever we measure 1 and a tile on the pile for 0 whenever we measure 0, we see a distribution emerge. This distribution is stable when you repeat the experiment under the same conditions. From that, you can conclude that the qubit, once prepared, seems to carry probabilities for measuring 0 or 1. In other words, the qubit behaves like a rigged slot machine. Each shot looks random, but with a fixed bias. Multiple measurements reveal underlying probabilities for 0 or 1. That is what people mean when they say a qubit can be both 0 and 1 at the same time. It carries probabilities for both outcomes. This phenomenon is called superposition, meaning that in the qubit both states, 0 and 1, are present simultaneously. Not as classical values, but as probabilities that only reveal themselves when we measure. And that is still not the full picture. For each state, 0 or 1, the qubit does not just hold a probability, it also carries a phase. So there is a probability and a phase for state 0, and a probability and a phase for state 1. This phase cannot be measured directly, not through single nor through multiple measurements. The phase only shows its effect when qubit states interact. When you combine the 0 or 1 states in probability paths of a quantum gate, their relative phases determine whether the probabilities add up or cancel out. Opposite phases subtract and reduce the probabilities. Matching phases reinforce and increase them. This is the underlying principle of quantum interference. Interference is the logical consequence of the existence of phases in qubit states. No phases, no interference. This is the full quantum state. Each basis state has both a probability of being measured and a phase attached to it. Mathematically, the probability and the phase of each state are represented by the so-called probability amplitude. This is a complex number with a real and an imaginary part. The squared magnitude of the amplitude gives the probability of measuring the state, and its angle in polar coordinates gives the phase. For more on interference, check out video 5 on quantum interference on my website qubit-lab.ch. So, in summary, a classical bit can hold exactly one of two possible values, 0 or 1. A qubit, on the other hand, can hold infinitely many possible states. These are determined by two continuous parameters. One defines the probability distribution between 0 and 1, and the other defines the relative phase between them. Remember at the beginning I mentioned quantum machine learning. Now you can see why qubits are so powerful for it. If you'd like to dive deeper, I explain this step by step in my quantum machine learning video number 9. I hope this shed some light on what a qubit really is. Let me know if it was helpful, or if you have ideas for improvements or other questions you would like me to cover. I'd love to hear your thoughts or questions. And of course, press the like button and do visit qubit-lab.ch. There you will find more material, videos, Python scripts, finance use cases, and much more. Have a great day.